Welcome to another edition of the Berlin Functional Programming Group. Today, I am pleased to introduce my friend, Joe Kachmar. Joe is an extremely talented programmer and engineer, and I have some notes. I have his bio, but really I can just speak from the heart. He, to me, was one of the primary reasons that my first Haskell study group in New York City was a success. I think he will probably want to offer me some kind of praise or credit for getting him started in the Haskell world, and that's really nice of him. But from my point of view, it was completely mutual. This Haskell group would not have been successful had people not shown up week after week and done the work and helped the other people in the group, helped me. This was a group endeavor. We figured out Haskell together. We grew to love Haskell together. It just so happens that Joe has gone on to write Haskell professionally, and he's not the only one from this group. I mean, I start to think of this group in somewhat mythic terms, this Haskell study group from 2016 to 2017 that ran for over 30 weeks. It ran so long, in the middle of the study group, I got married and moved to Germany, and it continued without me to its conclusion. So I have very fond memories of Joe from when I was living in New York and learning Haskell and going out to drink after learning Haskell. I mean, what else can I say by way of bio? Joe used to work for NASA. I believe he built rocket ships. So he has the perspective of a true engineer. And for whatever reason, he decided to sell his soul and write software instead. But we are here to benefit tonight from his enthusiasm and curiosity because he has, for some reason, decided to learn about the GHC internals to the extent that he is prepared to present to you about a topic I have never heard about, Levity Polymorphism. So I hope that I have injected a small amount of levity into the introduction. I'm sure that Joe is going to give us a serious and fascinating about this topic. I hope you all have questions. You better have questions for my friend Joe. They better be good questions. Put them in the chat and I will call on you when it's convenient and let you unmute and ask your question. And I'm sure Joe will be happy to answer all of them as we go and at the end of the talk. So that's my introduction. Please enjoy this talk by my friend Joe. It's all yours.
Well, thank you for that introduction, Stephen. That's a lot to live up to. Hopefully, everyone here can kind of enjoy what I've prepared. This is a topic that I've been interested in for quite some time. I've been probably reading about Levity polymorphism, some of the papers associated with it, some of the bits inside GHC, just for, I want to say, the past 6 or 8 months or so. And I've been kind of wanting to give a talk on it, but it's been hard to figure out the right way to present the information. And so when I heard that Steve was doing this series of remote meetups, I figured that this would actually be a really good way to motivate myself to collect this knowledge and then hopefully maybe impart some actual understanding onto other people. I've been sort of trying to make sure that the things that I've internalized have been represented sort of well in my slides, but like Steve said, please feel free to, at any point in time, ask a question if something's not clear. I've got a little break in the middle where I can kind of take some questions on one topic before going into a couple of the other sort of lower level things. So let me share my screen. Okay, can you guys all see that? Great. So levity polymorphism in Haskell, and importantly, other things that don't get discussed very often. So this is kind of like a weird bit of Haskell that you don't normally see if you don't go looking for it. But then when you kind of maybe poke a little bit on the internals, you start to see things that are strange and maybe don't kind of make sense based on what you've seen in the language or some of the libraries so far. So oops. So first of all, a little bit of a preamble. This is kind of like a CYA thing for me. GHC is very advanced in like general. So I'm going to talk about some stuff that's maybe low level and kind of make statements about memory layout and like stack versus heap allocation and things like that. At any point in time, GHC might look at your high level code that you don't think is super optimized and say, actually, I know how to make this super efficient, and then do it anyway. So everything in this talk is going to kind of come with a caveat that the GHC optimizer or the GHC specializer could look at your normal high level code and then say, actually, that could be made a little bit better, and then do so. And as another point, a lot of what I'm going to talk about is still sort of being actively researched and actively developed. At the end, I'm going to kind of go over a couple of open GHC proposals or closed GHC proposals that are going to see, development and implementation sometime soon. But, this is sort of a brief summary of where we're at now, not necessarily where Haskell was a couple years ago or where it will be even next year. And then the last one, I am not an active user of all of these features. I'm just sort of an interested party. So trust but verify. If you're ever planning on using some of this stuff in production or in active code, ask a couple of questions that can maybe point you a way to verify some of this stuff in general. But, this is, I've tried to make myself as knowledgeable about this as I can, but there's always going to be things that slip through the cracks. So, all right, starting off, Haskell in general, what is it sort of good for? The language is known for being, pure, functional, statically typed, and so on. But I think that the things that are of particular interest to this talk are the fact that Haskell is lazy. It's generally sort of considered to be a high-level programming language, maybe more akin to Python or Scala than, say, assembly language or C. And it's higher kinded. We're going to get to sort of what higher kinded really means in a little bit. But what it's not really being, what it's not really known for is being easy to reason about in terms of like space and time complexity. And like a big part of this is a consequence of the fact that the language is lazy. It's hard to necessarily know exactly what a program is going to be doing when part of how you're going to be writing your program is relying on the fact that the compiler might choose not to allocate certain things or even do certain tasks until you actually need them. So as a result, maybe you don't quite know what the complexity of a sorting operation is, because maybe not all those elements will get touched. Or something like that. And then it's also not really known for providing precise tools to manage memory allocation. This isn't Haskell specific. This is sort of a consequence of high-level languages in general. I would say most people probably don't end up being worried about the sort of precise language of how Ruby or Python are going to handle memory allocation and memory layout in their programs. But sort of all of these things are kind of interrelated a little bit. And so to kind of start off, I want to talk about the relationship between laziness, lifted types, and this concept of Levity polymorphism itself. So for the sake of example, let's kind of in Haskell define our own Boolean data type. And so in this case, we just say that you can have a Boolean type who can have like a value. So if you use this value keyword false to construct a Boolean, then you can see here when you ask the Haskell REPL, the type of false is Boolean. But what you also get when you do this declaration is you tell GHC that Boolean is a type whose kind is type. So this is kind of weird. What I'm going to say here is that, whoops, like when I say this type in sort of lowercase italicized format, I'm sort of talking about the conceptual notion of what a type is. And when you see this type that I'm returning in the REPL and that I've kind of put here in monospace code font, that's GHC actually as a construct called type. And so when we talk about Haskell being higher kinded, we talk about the fact that Haskell has this notion that there are types of types. And so, yeah, it's sort of weird. You can, I guess, say that kinds are types of types, and sort of like Boolean is a type of this value false. And so sort of kind of see how this interacts with each other. If I make a list of Booleans and I insert an error here, and I take the first element of the list, then I can get that first element out without triggering the error. So when you construct values in Haskell, things that throw exceptions, things that throw impure exceptions like error, undefined, or things like that aren't evaluated when the thing is defined, unlike, say, Python or C or what have you. And if you don't touch the thing that produces the error, then Haskell is perfectly happy to let it just kind of exist there and not ever be evaluated. But if you do touch it, so in this case, you use tail to drop the head and then get a list of just error, and then you take that element out of there, then you do get the exception. And this is kind of built around the idea that Haskell doesn't want to do any more work than it absolutely has to. So what we wrote was data Boolean equals true or false. And when you write something like that, naively, the first assumption is going to be that, well, yeah, Booleans are values, that may be one of true or false. But what Haskell actually provides us with is Booleans are values that may be one of true, false, or this little symbol here that means bottom. And bottom is the sort of representation of computations which never actually successfully complete. You can think of that as an exception or like any other kind of thing. It's basically the idea of because the language is lazily evaluated, behind any kind of door, you might open it up and then there's bottom because something blew up. And so it's sort of pervasive. It's most frequently a result of something like undefined or error. You kind of see those in partial functions like I showed earlier, where if you try and take the head of a list, what do you do if the list is empty? Or what do you do if the list has an error inside of it? But this kind of raises the question of like, what actually is a type? So, you know, if a type isn't what we wrote, if a type is what we wrote plus this extra little bit of stuff, then how is it actually represented in GHC? And this is where things kind of get like a little weird. What we see as type in like signatures and Haskell and things like that is actually a type alias with some kind of fiddly magic inside of GHC to not actually represent this as a type alias for this other construct called type in all caps. And type is a higher kinded type that is parameterized by something of kind runtime representation. And so this is basically a way of saying that when you have any type in Haskell, it's actually a thing that has a parameter inside of it that tells you how it should be represented. And so the most common form is this type thing that we saw earlier, which is of type lifted rep. And what that means is that type lifted rep are lifted types, and lifted types are types of lazy values. But the cool part here is that there's a mechanism in Haskell basically to have different sort of kinds of types. And so in addition to just lifted representations or lazy values, which is what we saw earlier, Haskell also provides unlifted types. And so you can see here one of the other options is like an unlifted rep. And this is sort of neat because now we can talk about types that are strict, but like types that can't contain bottom at all, types that can't be lazy, types that you sort of make strong statements about their representation and their sort of like how they kind of exist in the computer. And sort of beyond that, you can see here this sort of like this, I haven't included all the types of runtime rep because it would kind of run off the slide, but one of the other ones is there's this int8 rep, which is kind of neat because Haskell can also, instead of just representing things in terms of lifted or unlifted types, can make precise statements about things like, maybe this thing is going to be an unlifted 8-bit signed integer. And so you can make a very, very careful and precise statement about what the actual value you're going to be operating over is. And so just to kind of illustrate by way of example, if you look in Haskell's prelude, you're going to see this dollar function. It's kind of one of the first things that people run into when they're writing Haskell. And dollars were sort of represented by this. If you provide it an f of type A to B and a value of type A, it applies A to F and then returns a B. And what this is sort of actually doing under the hood, if you dig into how dollar is implemented, is it's doing this thing, which is sort of saying that for all, so it's saying for any R and A, where R is the runtime representation of the type of B, take a function that goes from A to B, take an A, and then return a B. And so sort of trying to explain what this is doing is it's saying that A, that's a type. R, that is any runtime representation. And B is a type that can have any representation under the hood in general. And this is sort of like the crux of what Levity polymorphism is. It's a way of saying you can write functions that don't necessarily care about how they're being represented under the hood. Or you can write functions that are sort of polymorphic over whether or not they're lazy, strict, integers, floats, but like at a more fundamental level than just the normal polymorphism, it's polymorphism over how these things are actually represented on the computer. There's some sort of caveats to all of this.
Joe,
Mm-hmm.
we have a question about bottom values from Ulrich. So
yeah, what's up?
Ulrich, go ahead.
Yeah, as you just gave that brief example that bottom can basically inhabit any value, I thought I've heard that before in other languages where it's called null or nil or something like that. And we always say in Haskell it doesn't exist. But this looks like well, you don't use it, you don't test for it, but it's still possible to be there. So what's the exact difference from null?
I mean, I would say that you don't, like, the exact difference is a lot of the fact that you don't encourage people to use it. I would say that if someone's using undefined to talk about something in the same way that someone might be using nil in, say, like Go or C or Clojure or what have you, that would be an anti-pattern within the language.
But it's not inhibited by the language. No? I mean,
yeah, I mean,
it's there.
Fundamentally, some notion of this computation might not succeed has to exist, right? Like you can't solve the, I mean, you can't like prove that a programming language is going to terminate. Or at least you can't prove that Haskell is going to terminate. There's some Turing incomplete languages,
yeah,
like DAL or whatever, that kind of get around this, but you kind of do need something. So yeah, this is kind of like one of those weird fuzzy bits. I would say that this is one of those cases where the culture of a programming language is very significant in that you have tools like maybe and you have tools like either, and that allows people to express the things that they would commonly express with nil or null in other languages, and so it gets avoided. And so even though bottom exists, it's very much in, I would say, idiomatic, well-written Haskell code reserved for truly exceptional cases, or cases where you're kind of going to make a statement that this thing really should not happen. Yeah, I'm sorry if that's not super satisfying.
But does the fact that it exists get in the way of any sort of, if you want to prove something actually, because then you have to take it into account all the way, right?
That is a bit of a can of worms. I will say that yes, it does get in the way, because I mean, a good example is, say you want to do something that operates over a list, and you have a whole bunch of functions in the sort of Haskell standard prelude that are partial with respect to lists, which means that if you call, you know, from this example earlier, head on an empty list, you're going to get an error. And so you kind of do have to work around this in some cases. And the language itself has things in there for it. So like there's functions that you can use to kind of try and force evaluation to see if any bottom values exist. I will say, in my experience, it's one of those things that you run into much less frequently than other languages where null and nil are first class patterns, because this is something where, you know, if you're using an error or you're using an undefined and it comes up in code review in a professional Haskell code base, you're typically going to be asked to justify your utilization of it. Whereas if you're using nil in another programming language, I don't think that that's going to be terribly common, because it's something that you're going to be using fairly frequently. Does that make sense?
Yep, thanks. Okay.
Yeah, I guess it's worth saying it's not like a value that you would ever actually use, because as soon as it's evaluated, your program explodes, right? It's not like you would say, if something equals bottom, then branch in this way, otherwise branch in some other way. Like in many languages where you just sort of pass these things around and use it. You would never do this in Haskell.
Can I add some theoretical input on this?
If it's very quick.
Yeah, it's quite quick. So the main thing, main difference to nil is you can't pattern match on bottom. And so bottom represents both terminations that cannot, like in theory, it represents both evaluations that possibly do not terminate and evaluations that terminate with an error, like undefined and the stars. And then the other question, which was if there's an error that happens with undefined, there is actually, if you try to look at isomorphisms between types. For example, maybe should in theory be isomorphic to either where left is represented by just the unit type. But actually, there are two representations with different levels in which bottom can occur, right? Because maybe just has the nothing constructor, and that can be undefined. But if you represent the nothing constructor with either unit, then you could have the whole either unit be a value of undefined, or you could have the constructor left exist, but then the unit value you replace with undefined. So there's kind of a bit of a theoretical problem with these isomorphisms. But yeah, that was my input that I wanted to add.
Thank you.
Cool. Yeah, good discussion, but let's let Joe get back on track. Thanks, Joe.
Yeah. So there are a couple of other sort of weird things that come along with it. And these are, some of these are kind of like fundamental issues that I'm going to get into in the next section where we talk about memory representation, but Levity polymorphic values. So this thing here where you see this, this value B, Levity polymorphic values can't be bound. And what that means is if you have, you know, fn0x equals whatever, or let x equals whatever, x can't be polymorphic in its runtime representation. X can be lifted rep or unlifted rep or things like that. You can make bindings where you don't just have lifted types, but if GHC doesn't know what the runtime representation of something is supposed to be, it can't know how to represent that thing when you try and bind it. So all it can really sort of be is this opaque box that you can do stuff with. And we look and see how function is doing. That's kind of what it's doing here. It's saying that I can deal with an F whose return argument can be anything, but it doesn't actually ever touch that anything there. It's more just sort of like a thing to pass around. The other sort of gotcha is that unlifted types explicitly cannot be bound at the top level. So if you imagine a module and you were to try and write something like fn1 has a of type unlifted rep, that's illegal. That sort of might change, but the general idea is just that Haskell doesn't really have GHC doesn't really have a way in which it's set up to represent that concept as like a thing that exists in memory. And then the last one is that error messages and type signatures can be confusing, and you can sort of see this here by example. This is a type signature that most people who are beginner to intermediate familiarity with Haskell can sort of follow along with, and this is just kind of a mess. I mean, this has got like rank n polymorphism and data kinds and other confusing things there that aren't super straightforward. So just sort of like a brief recap of this part. Haskell as a language is lazy. Lazy values are lifted. Strict values are unlifted. And then conceptually, Levity polymorphism is the way in which Haskell gives us a language to talk about the distinction between this lifting and unlifting so that we can write programs that are precise about the sort of representation of their types as constructs in memory, and in terms of whether or not they are things that sort of have this bottom value living inside of them. I wanted to just sort of, before we get into the next section, also see if there's any questions or people maybe had, weren't particularly clear about a couple of things over there, because the next part's going to be a bit more complicated when we talk about stack and heap allocation and sort of memory representations.
Yeah, there seems to be a question about lifted versus unlifted types. Ulrich again.
I think I just started a discussion. I had a very simple picture in mind that lifted means basically the same as boxed. You have a pointer to some location in memory, and unlifted is like just a raw value that you can stick into a processor register.
We're gonna get into that. That's actually the next section.
Okay.
So I'm going to try and answer that one. But
Cool,
there is a relationship there. It's not quite that simple because of course it isn't. But yeah, there is a relationship there. Anything else?
I don't see anything else, but as they flow in, I will continue to interrupt you.
All right. Well, so on Ulrich's earlier point, runtime representation and memory allocation. So from Wikipedia, so calling conventions, kind of sort of a way in which you can identify how subroutines kind of receive parameters from their caller and how they sort of return their results. Basically how things end up being organized in the computer's memory layout, registers, heap memory, stack memory, and things like that. So runtime representation doesn't just abstract over the lifted or unlifted nature of values in Haskell. It also abstracts over the calling convention of functions. And what that means is that in addition to lifted rep and unlifted rep, there is that int8 rep from before, as well as tuple rep, which is the type of sort of unlifted unboxed tuples, and sum rep, which is the type of unlifted unboxed sum types. And then these two can sort of be further parameterized. And so this is also another sort of interesting thing where you can say that if you have a runtime rep that is a tuple rep, it also is going to be parameterized by a list of runtime representations. So it's saying that this tuple value that may sort of exist as this chunk of memory is going to also have some information about it, where those may also be lifted, unlifted, or other particularly precisely sort of specified pieces of type information. And so now we get into some sort of other rules. Lifted types must be boxed. And sort of what boxing means here is that they're represented by pointers to heap allocated objects. And part of this is because if you have a lazy value, it could be something else entirely. So you need a little bit of indirection to sort of actually represent that on a computer. unboxed values must be unlifted, which is to say that if you have an integer that is not supposed to be heap allocated, so an integer that's supposed to be stack allocated, it can't be lazy because you have no way of representing the laziness. Because if you tell the computer, I'm giving you an int, it's going to have an int. It has no way of saying that this thing is actually something of some other type that might be bottom or might be some other kind of exception. However, unlifted structures may contain lifted values. So an example of this is this sort of array hash construct, where it is an unlifted array. So the array itself is guaranteed to be strictly evaluated, but it contains lifted integers. And so the representation, if you sort of imagine this in your mind, is a pointer to an array object on the heap, and those array objects are going to, that array object is going to contain pointers to integers which may or may not be, may or may not contain undefined. So they're potentially lazy. And so, like, why do we care about this? Well, unboxed values come with guarantees that are actually very interesting. So like I said before, this might all be completely optimized away, and in very simple cases, GHC actually does optimize this away quite well. But the reason why it's useful is because Haskell is now exposing a language to us that allows us to very precisely make statements about what our programs are doing, and we can use that in areas where, you know, we might otherwise use a foreign function interface to a language like C. So we can make statements about things like static memory representation, like, are these things going to be stack allocated, or can these things be, you know, stored directly in register memory rather than, you know, somewhere else? And like, can we make statements about programs that are going to be deterministic, or very strong statements about their efficiency in some other ways? So this is sort of like an example of a program that's very low level in Haskell, but sort of exhibits all of these things. There's actually a typo, I apologize. This is meant to also be a hash, and this is sort of not meant to be there. The way that this function works is int64 hash is a way of saying this is a 64-bit signed integer. This is also a 64-bit signed integer, and this is a function that can only add two 64-bit signed integers. So these are all sort of stack allocated signed integer constructs. And then this is sort of what's called a primop wrapper, where if you go to this link down below on primops, this is sort of a thing that Haskell exposes that sort of directly links down directly to the, what's the way to say it? The runtime that GHC uses to execute Haskell code defines this directly and then exposes this wrapper so that you can call it at a high level. But this is sort of a deeply magical, very primitive thing in the language. Just sort of give you an idea about what this looks like. You can plug the function that I wrote earlier into Matt Godbolt's Compiler Explorer, which if you've never used is actually really cool as a tool. There's a Haskell backend. And so you can see here that that function in green, this little green highlighting background here, compiles down to these assembly instructions and nothing else. So this is sort of a very, very silly example, but it kind of shows you that you can write code in Haskell that ends up just being 3 instructions and that's it. And so kind of just to keep tugging on this thread a little bit.
Joe, I've got a few more questions, but they're very small ones.
Yeah.
So first, may an unboxed type be lifted?
No, unboxed types must be unlifted.
Okay, and then are the guarantees here part of the Haskell report, or are they specific to GHC?
Yeah, so I've been trying to, in the slides, call out GHC specifically, but I probably should have said that earlier. Everything that I'm talking about here is GHC specific. I haven't deeply studied the Haskell report to sort of be able to make any kind of declarative statements on what is, you know, Haskell report specified and what is implementation specified, but all of these things come from GHC specific module exports, and a lot of them are tied very directly to GHC's runtime implementation. I mean, the primop stuff specifically is coming from stuff that GHC directly implements in terms of sort of machine characteristics. So I would assume everything that we're talking about here is mostly going to be GHC specific.
Okay, that's it for now.
Okay, so some other sort of interesting things here. unboxed tuples. So this is a normal Haskell tuple, and its representation, modulo optimizations or anything like that, is going to be a pointer to a heap object whose inhabitants are also going to be pointers to heap objects. There's like a fair bit of indirection going around here. But you could also have this unboxed tuple, and this is the syntax for unboxed tuples. It's just this little hash to the sort of left and right, to the right and left of the opening and closing parens. And what this basically lets you do is say, I have a piece of memory that has two pointers that are contiguous in how they're laid out, and then those point to those heap allocated ints, which may have that sort of indirection about laziness. And this is kind of neat because my understanding of it is that the GHC is going to try very, very hard to be realistic about this. And so now you basically have a way of saying, I have this chunk of memory that's just two side-by-side pointers. Or you could say you have an unboxed tuple of unboxed ints. And then these are going to be two machine-sized integers in contiguous memory. And so like this is really a zero-cost abstraction in a very high-level language. We now have a way to write Haskell, but also to be able to say things like, okay, GHC, give me things that are literally just two adjacent bytes. And there's like a whole bunch of magic that goes on behind the scenes where GHC actually can turn this representation into this representation for very simple things. So I'd be very surprised if you were to ever write int comma int, if GHC didn't just turn it directly into this representation, and that ended up being two contiguous pointers or two contiguous machine integers. Likewise, though, there's also sort of a language for representing unboxed sum types. So normal sum type, again, all pointer indirected as with the tuples were, there's a little bit of a typo. There should be enter double and enter double. But similar to tuples, there's this notion of having this kind of hash and then paren to identify this sort of unboxed sum structure, the pipes like normal sums. And we can say that int or float hash is an alias for an unboxed sum that may be a 64-bit int, a double, or a 64-bit word. And I chose these specifically because these are all going to be the same size anyway. And so GHC should be able to, on 64-bit architectures, optimize this into 3 words. A tag word, which identifies which constructor this thing is. Something called the info table pointer that I linked to down below, but I'm sort of not gonna go into too much here. It's just specific pieces of information that GHC uses to do certain things, information about functions and such. And then the data word containing the actual data.
We have another question, Joe. Sorry to interrupt. Anirban has a question about the previous slide. Anirban, why don't you ask your question? I'm not sure what it is exactly.
Yeah. So the question is, there are 3 definitions, right? The third definition, is it going to take place in stack or in heap?
This one should take place in the stack. This should be stack allocated because there's nothing in here that should be backed by a pointer. So this is an unboxed unlifted type, or this is an unboxed type, and so by definition is unlifted. And then these are 2 unboxed integers, which are also by definition unlifted. So GHC should be able to represent this all statically. And in fact, the paper introducing Levity Polymorphism uses this as an example where these things really should just be 2 adjacent pieces of memory.
Okay, so the above 2 ones are going to be heap allocated, whereas the third one is going to be always stack allocated. That's the conclusion.
Yes, it should be. And again, I really do want to emphasize this though. GHC will very aggressively try and optimize everything that it can, and the optimizer is very, very, very good. And so this is more of this should be guaranteed to be stack allocated, whereas these 2 could be inlined or could be, but like they might, not be.
Cool, thank you, sir.
It's probably worth saying that you would generally not write your programs with this stuff, but it's fun to know about, right?
So there are a couple of other examples at the end that I'm going to kind of go through and show some of the code listings. But there are a couple of instances where you could write your programs with this and they do confer some interesting benefits. So I've got examples of real code at the end for it.
In the meantime, we have a few more questions. So Hamid, do you have a question?
Hey guys. Yeah, I just want to know that
if I'm using this sharp, can I use it in my Haskell programs, or this is going to be generated for GHC core?
This is something you can use in your Haskell program. Sorry, I guess I maybe should have also said that. There's a bit at the end where I'm going to talk about some of the things that you would need to do, like language extensions that enable some of these features. But yes, these are things you can use in your Haskell programs. And I'm going to, like I said, probably also try and show a couple examples of how these are used in real world Haskell programs, the types of benefits that they confer.
Awesome, thank you.
And one more from Artem, if Artem would like to ask. Artem, I can ask myself. Artem suggests that you explain a bit. No, Artem doesn't have a mic. Maybe explain a bit what is the stack in GHC. Yeah, I suppose that means stack versus heap in this context.
Yeah, in this case, I'm talking about stack versus heap allocation. So I don't want to give a like good, proper principled explanation of the difference between stack and heap memory on video, because I'll get it wrong and then someone in the internet will correct me. But in general, I think a good way to think about this is memory that you know about statically versus memory that can be dynamically expanded or contracted. So when I say like this representation here of unboxed tuple of unboxed ints is going to be stack allocated, what I mean is that like there's going to be no pointer to an object living in some other chunk of memory. It's going to be like when you call a function that needs to use these things, it's going to have direct access to this piece of memory rather than having to chase a pointer to actually get to it. I'm sorry if that's not the best explanation. Yeah, this is one of the weird things about this where I don't really feel confident that I'd be able to give like a good explanation to someone who's not familiar with these concepts.
Sounds pretty airtight to me, Joe. And don't worry, I have disabled YouTube comments.
All right, well, good to know.
Okay, Artem has a follow-up, and let's maybe make this the last one so that you can continue. Isn't it word granular, so no way to store bytes and shorts?
It isn't, I guess, what word granular?
The stack.
So I believe, but I need to consult something for this, that there are, so if you look back here, there are.
Oh, somebody has unmuted. Okay.
Okay, well, just as like a comment here, I believe, but I need to consult like a manual or something. There are notions of like this int 8 rep, and there is a thing that GHC does, an optimization I'm going to go over at the end, where it can sort of reorder and pack things in so that they aren't necessarily all just like rounded up to the word size. But that one I would.
I think memory alignment and bit packing might start to get out of scope for you.
Yeah.
But it's fun to know about.
Yeah. So this is kind of like an example of how these things get used. If you're familiar with maybe in Haskell, there exists this notion of sort of like a zero cost maybe, or like a much lower cost maybe, where we can say maybe hash is a type alias for an unboxed sum where one element may be some a value, which could be lifted, and the other one is this empty tuple, which is nothing. Like literally, it just doesn't exist. And we can use this feature called pattern synonyms to basically say this is what a constructor for a just is, where it's just going to insert that value on this sort of like left-hand side of the sum, and then this is going to be a constructor for a nothing value, which really is just gone, it's erased. And so like you can use some of these features to create higher level abstractions in Haskell built off of these very low level sort of building blocks to sort of get somewhere. And kind of like I was saying before, maybe you should have put this a little bit earlier, but to use this type of thing in Haskell code, there are these language extensions. One is magic hash. That is actually what it's called. And all it does is it basically lets you use this hash postfix in names of things. So this int64 hash is a type constructor for unboxed 64-bit integers, and this I64 hash is a data constructor for 64-bit integers. And so it has this type here where you feed it an int hash, and it spits out this like lifted 64-bit int. And then to use a lot of this stuff, you're going to want to import ghc.exts, which is sort of these approved re-exports from the ghc prim module. So ghc prim, I mean, the terminology is just, it's not approved. You're encouraged to import from ghc exts. I think this module hierarchy might change a little bit more frequently. So there's a couple of other things I kind of wanted to go through if you felt that we had time, Steve, and if people were interested, where there are some actual code examples of some of the stuff being used.
We have all the time that you need.
Yeah, so, whoops, let me, all right, can you still see this? Okay, yeah, you can, cool.
Yeah,
so,
yes, we can see it.
So just to give you an idea about maybe what this sort of looks like, Daniel Cartwright, Chesai, has a sort of take on what a Levity polymorphic base in Haskell would look like, where you have these notions of like, well, maybe there's actually a better example in Monoid, but you can write type classes that are Levity polymorphic. Yeah, so you could basically say a monoid that would work over, you know, things like int64 or things like that. And you get this kind of weirdness where, because of that restriction I said earlier, you can't have a Levity polymorphic value sort of that exists at the high level. You have to do this thing where it takes a unit and then returns an A. And then this sort of actually ends up compiling down to that pointer interaction where GHC can say, I don't have a thing like an int8 or something like that. I actually have a pointer to something somewhere else. But so like, this is sort of an example of maybe what a sketch would look like of Levity polymorphic versions of things that we see commonly in Haskell. I think that one of the really cool examples of this, the thing that actually made me interested in reading up on this in the first place is Ed Kmet has a project called Codex, and in Codex he's got a parser combinators library that he's called Parsnip. And the thing that I think Kmet was trying to do here is he wanted to make a very, very, very fast parser explicitly for like ANSI values. So not Unicode, it's going to ignore a bunch of the common, like the complicated stuff of text, but it has in here some of these things we talked about earlier, where he's got like this result, which is sort of like, well, he's got this, here we go, this option here, which is like that unboxed maybe I showed, and a whole bunch of this complicated code for actually implementing a parser. But the cool part here is that he can have these parsers that are really just these collections of unboxed types. And then he can implement sort of the higher level constructs we're familiar with in Haskell. So functor, applicative, and monad. And so, and alternative and all that stuff. And so the cool thing here is that this is a parser combinators library. And so you could write parser combinators like you might write for something like parsec, if you're familiar with those. And under the hood, this really ends up just taking a byte string, copying that byte string to be a single chunk of memory, and then incrementing a pointer through it to try and pull out chunks of memory to parse into things. And so like under the hood, this is really just going to be extremely fast, extremely memory efficient. But from the point of view of you, a user, you would be able to just use standard combinators like try or like word8 or like the alt or like the applicative things for writing your parser combinators. And so like, I think the real power of this abstraction and the things that this enables are, you can have somebody like Ed Kmet, or, you know, probably if you're most people, someone not quite as smart as Ed Kmet, but getting there, put together all of these low-level abstractions that are backed by unboxed types or backed by these sort of Levity polymorphic things, but only exposed to you a higher level interface, and use those and then have a very strong feeling that it's going to be very fast and very efficient. If I'm remembering right, I think Kmet was using this for a like parsing GLSL to render things sort of in real time, where we wanted to change shaders on disk and have the parser basically be able to re-render that very quickly. Let me see. The other thing that I wanted to talk about that I thought was maybe kind of neat, and this is sort of getting into the miscellaneous and other kind of stuff I thought was cool, is this concept of something called unitarization in GHC. And this one is actually not documented, as far as I can tell, anywhere outside of the GHC source, and this one issue that Chesai put together. But unitarization is this very neat thing in Haskell where if you have an unboxed tuple type, GHC will turn that unboxed tuple type, or sorry, if you have an unboxed sum, GHC will turn that unboxed sum type into an unboxed tuple where so like say you have this this int or int or int or byte array, or say you have this int or tuple of ints or int, GHC will be able to say, oh, well, I know that since the largest thing is going to be two ints side by side, I can turn this whole representation into something that is only the tag value and then the two remaining values that actually provide all of my data. So there's all of this this cool stuff that GHC does under the hood, where it can basically say, you know, naively, if this were implemented, this would be 1, 2, 3 integers plus the byte array, whereas actually you end up with a single integer and a byte array and sort of these rubbish values depending on the actual alignment size of the underlying words. And so I've included some of these links as well. There's a whole bunch of stuff that's really only defined in terms of the proposals or GHC source code itself. But yeah, that's kind of most of what I had. The stuff at the end are things that I'm still kind of trying to get a handle on the right way to explain to people. So it's a little sort of frantic, but yeah, that's most of this. Did you guys have any other questions?
So I'm asking now if anyone has questions in the chat, so go ahead and drop them in there. Okay. Ulrich. Ulrich, I think, is my #1 question asker across all of my meetups. So Ulrich, please go ahead.
Yeah, I was basically thinking that all of this very smart, low-level type mangling and so on. What are the specific assumptions you need to put in that the compiler can't figure out by itself? I mean, typically we use compilers to not need to do these kind of things, right? And now I feel like we're going back to writing assembly, sort of comparatively, like you build abstractions, you have compilers to do smart stuff, and then you go back to do assembly because you say, yeah, but the compiler is slow. So yeah, what's the difference?
So like I said, and again, I really can't emphasize this enough, GHC is smart, and like 99 times out of 100, you won't need to worry about any of this. We do use compilers because compilers are smarter than us. And the unitarization thing is, as an example, I think is a really good one where you don't need to do things like, I mean, I'm gonna pick on Go a little bit because that's a popular thing for Haskellers to do, but there's like a linter for the Go programming language called maligned, where it'll look at your struct and it'll see the ordering of sort of elements that are in a particular Go struct, and then give you a linter error if you could reorder them such that they would be more efficient in memory. And like GHC does that entirely. And GHC goes beyond that. And like for some types, it'll not only do that reordering, but it will do like the whole packing the representation down to make it even more efficient. And like at this proposal here, under the unlifted data types sort of discussion, GHC will take, I believe anyway, there's a note here saying that it's not quite implemented, but I think this did get implemented. GHC will be able to take, you know, not explicitly boxed sum type representations and then turn those into those unboxed and then unitarized versions under the hood anyway. And I guess maybe there's one thing I want to emphasize. As cool and interesting as I found all of these low-level abstractions to be, they shouldn't be necessary, and GHC should do the right thing most of the time. Like, they exist so that when you need to make a statement about how something will execute definitively, like say, for example, you are writing a like network programming library, and you need to be very, very careful about how memory is allocated and about how fast things are, because you're going to be backing programs that people are expecting to be very performant. You can do that. I think it's less about requiring people to do this to write fast code and more about saying, if you absolutely need certain guarantees about your code, these tools are here for you to use. So yeah, I mean, I don't know, do you feel like that kind of answered your question? I would say that GHC is not any less powerful for having this, and it doesn't force people to use these tools if they want fast code, because the GHC implementers are very frequently using these features to improve code generation and to sort of improve interpretation of higher level stuff down to this. But it's more that if you feel like you need to, this toolkit is available to you.
Yeah, okay. So the specific example you showed with the parsers, there is a very specific assumption you stick in, because you say you limit your character set. And because of that, you can do certain additional optimizations that the compiler doesn't know about, because he doesn't know about the specific assumptions. And that things you showed basically gives you the tools to benefit from these additional constraints for your specific problem.
Yep, that's one example. And then I think the other one is for all of the stuff where we talk about unlifted data specifically. I mean, you basically are starting to get a toolkit in Haskell for being able to write code that you can now say is completely strict, which kind of feels weird because most programming languages aren't lazy, but it's a very powerful tool in Haskell itself, because now we have at our disposal a language that is lazy by default, but then maybe perhaps we can start writing code that is strict and like does make very measured, precise statements about how memory is going to be used and what sort of space and time complexity are. So you could do things like write low-level socket programming libraries in Haskell without having to rely on C so heavily. And other kind of low-level libraries where you can lean on Haskell's type system, but also still know that it's going to be extremely efficient.
If I may hijack that with one more question, so how does what you showed now compare to things like bang operators where you can enforce strictness?
A bang operator, so a bang operator is going to enforce strictness where you apply it, but an unlifted data type is a data type that is strict throughout it. So like you can annotate your code with strictness annotations and then know that in those specific cases, those thunks are forced at that point, but it doesn't necessarily deeply force the evaluation of the entire structure. And more importantly, I don't think you have the guarantee that you have, which is with unlifted data, that you know that you're basically talking to something that can't contain bottom at all. I'm sorry that wasn't super helpful. I'm trying to think of maybe a better way to say that would be a bit clearer. I think maybe a better way to put it is, this gives you a language embedded in Haskell explicitly for talking about things that are not allowed to be lazy. Whereas bang patterns give you a way of saying, take this lazy code and then try and strictly evaluate it as much as you can, or try and strictly evaluate it at this point.
Okay, Anirban also has another question. Go ahead, Anirban.
Yeah, could you please circle back to the Ed Kemet's code where he was extensively using Levity polymorphism? Just like it couldn't completely comprehend that stuff.
Yeah, so there's a whole bunch of stuff going on here that I can't completely comprehend. So I'm gonna be able to give you limited advice on this, but this isn't so much Levity polymorphic necessarily as it is using these low-level unboxed constructs that I'm talking about. I guess what specifically are you curious about?
No, because I couldn't understand. So whatever you are saying, I'm 100% agreeing. So I do not see too much Levity polymorphism here. So it is like boxing and unboxing, like that kind of stuff. So like where exactly like the Levity polymorphism he's using? I'm not seeing he's using.
I don't necessarily know that there's any Levity polymorphism going on in here. It's more just that like this is an example of low-level Haskell, and that this is the type of thing where the fact that GHC exposes the sort of, like, Levity polymorphism allows us to talk about low-level and high-level constructs in Haskell together in the same language coherently. So I wouldn't say that he is necessarily using Levity polymorphism here, and more that, like, Levity polymorphism conceptually is what gives us a base to sort of, you know, in Haskell, the language, talk about both high-level and low-level code together, like using the same set of abstractions.
Right.
I like the ops, the fops, and the bops. Okay, let's see. Artem has a question, and I think I have to ask it myself. Could you tell a bit on when one can and can't have Levity polymorphic types, e.g. arguments or return type of a function?
Yeah, so the rules, as I understand them, are basically you can't return Levity polymorphic types. You can't, well, that's not true. You can't bind Levity polymorphic types. That's the, like, precise language. So the way of saying, if you have a function f and you want to pattern match on x, x can't be Levity polymorphic. Or if you have, you know, you want to do like a let binding inside of a function, that can't be Levity polymorphic. The way that I've sort of got this visualization in my mind is you can have a Levity polymorphic value that gets passed around, but you can't actually ever look at it. Like, if you ever try and turn it into something that really exists, like, you know, interrogate it, you're not allowed to. It really is this way of just saying, I have a thing here and it could be anything. Yeah.
Okay, I'm just seeing if Artem has a follow-up question for that. Nope. Any other questions? Just give people a chance. So have you actually been able to use any of these super advanced features in your own work, Joe?
No, this has mostly been the thing that I've kind of been poking around with for fun. Actually, there was another fun example that I had. This is not practically useful at all. This is very much like a silly thing. Where was this? No, it was after this one. So basically, you can pattern match on I/O using some of these tools. Well, I don't know where it went. I'll try and put a link in there. But basically, you can write code that goes into I/O. There we go. And unpacks it into these components. So I/O under the hood is actually this primitive state type where it's the primitive unlifted type of states. And it's a state type, it's a primitive state type with this token called real world, which is sort of like a thing that tells you the state of Haskell, the runtime at any point in time. And this token gets passed around, and that's how I/O can, you know, evaluate things in general. But when you're dealing with, I think actually maybe Commit might even do it here. When you're dealing with this kind of stuff, yeah, Control F on I/O is not super helpful. Yeah, here we go. You could do absolutely crazy, bizarre things like this, where I am patterned, like I'm opening up I/O, I'm getting the state token, and I'm doing things with it, like passing it around. Yeah, so I haven't had cause to use this directly in my work, but like this is the type of thing where when I was reading about it and I was kind of implementing little toy things, it forced me to see, well, I need to do this action that has an effect, and I want to use these kind of weird low-level constructs for it. How do I do that and not have I/O completely ruin my day? And the answer is you learn that you can pattern match on I/O and then pull values out and then pass them around like they're real things. Deeply magical, very strange.
Yeah, I mean, that offers a segue to my next question, which is, how did you get interested in this stuff? I mean, maybe it's kind of obvious. I mean, I would be interested in it too. It's always fun to know how things are implemented, how they work at a lower level, but maybe you could talk a little bit about how you ended up there.
Yeah, so like there's this tension, right? When you're writing computer programs between I would like things to be safe and I would like things to have low cognitive overhead, and I would like things to be efficient and I would like things to sort of be, I don't know, fast and small. And you kind of see this all over the place. Like it's very popular for people to talk about how they've taken something that they wrote in some high level garbage collected language and they rewrote it in Rust and now it's way faster because, you know, now they're using all sorts of things that are lower level, or I'll say lower cost abstractions. And you know, in the case of Rust, you actually don't lose a whole lot because the language is very well put together. But for a long time, if you wanted to do those types of things, you'd have to go down to a C foreign function interface or write things in C or C++ and not necessarily get the same guarantees. Or in C++'s case, get the same guarantees by writing some like absolutely truly warped template code to do stuff that's confusing and mortal people can't understand. And so I was kind of thinking, how far can we go in Haskell? And you kind of like pull that thread a little bit. Can this language, which is typically known for being high level and you know, the type system will try and take care of a lot of your problems for you, but at the cost of you might not have ways of precisely reasoning about space and time allocation. And I mean, like on that last topic in particular, Neil Mitchell has a very good blog post about how he tracks down a space leak in Haskell. Which is the type of thing that happens when you have a lot of lazy computations. Or like it can be a consequence of that. And doing like understanding how Haskell applications work in terms of their memory and time complexity is not trivial. And very, very advanced practitioners of the language still have problems with it. And so I kind of saw this as a, well, can we get a lot of the benefits of Haskell, higher kinded types, a lot of type safety, but can we also get it in a way that allows us to have a subset of the language that is still easy to reason about for these types of things? So we can write small chunks of Haskell programs that are tight loops. And so I think it's more of a, I'm personally interested in how far can we make computers go without trying to make things super unergonomic. And we're not quite there yet. I mean, like this is not necessarily what I would call ergonomic. You have to know quite a bit of weird corner case stuff and it looks kind of strange. But I think we're getting closer in that we're getting consistent bits of abstraction at various levels of Haskell, the language, that lets us talk about these things without becoming incoherent and without having lots of special corner cases. Like Levity Polymorphism was introduced because GHC needed to talk about the difference between these like unboxed, unlifted runtime values and normal types. But for the longest time, they just had hash as this magic kind. And so Richard Eisenberg actually, I think, did most of his work in GHC 8 that introduced Levity polymorphism. And then we unified this notion of talking about types that are polymorphic over the runtime representation. And so the stuff in the pipeline, I think, brings us closer to that.
Okay, you just answered a question that I didn't even know that I had, because I think mentally I must still be living in GHC 7 world, because I was still kind of thinking of them as kinds. So thanks for clearing that up. Hamid has a question about garbage collecting.
Yeah, so basically I want to know, can we assume that if we are going this way, maybe there will be no need for garbage collecting at some point?
No, we can't assume that, but I am unfortunately not. I don't want to. I can't give a definitive answer on that. The answer is no for lots of reasons in Haskell in particular. But well, okay. So maybe a better question. What do you mean specifically by that?
So what I'm saying right now is that you're basically putting everything you have in the stack, and there will be no heap in order to actually invoke the, I guess, the GHC, the garbage collection calls. So you don't need to have the garbage collection at a certain point.
You don't need to have it at certain points, but you're not putting everything on the stack. So like unboxed types can, or unlifted types can contain, or no, unboxed types can contain like pointers to the heap as an example. You know, like you can, like that array hash I showed earlier, that could have values that exist on the heap and are also lazy or things like that. And also like the garbage collection as a paradigm is very deeply ingrained in a Haskell language. I will say, in general, if you're curious about the garbage collection and sort of like, there's a paper that you might find interesting, which talks about the duality of garbage collection and atomic reference counting, that if you're interested in Haskell and you're interested in GC and potentially when GC may not be used, you might like. I'll try and find a link and then drop it somewhere. But I think the answer is no, I don't think we're going to see GHC without garbage collection for any amount of time in the future.
Okay, thank you.
I think people might be interested in knowing where they can find out more about this topic, Levity polymorphism, Haskell internals. I imagine a lot of it is just kind of digging around in source code and figuring it out for yourself, but maybe there are some resources you can point people toward.
Yeah, so I'm going to do the same thing that Alexis King did when she gave her talk over the weekend and say that you should definitely go check out the GHC users guide. It is very good. It has bits of stuff on all sorts of the things that I talked about today. It's fairly well written. It's fairly well updated. Beyond that, there are a whole bunch of GHC proposals that talk about this. There's a whole bunch of issues threads, and I don't really know if they're collated in the most convenient to find way. What I can try and do is put together a little reference guide of some of the stuff that I've been using to learn about this, and maybe post that on GitHub, or maybe pass that to someone else to post somewhere with a little bit more visibility. But unfortunately, a lot of this knowledge is, I mean, like the unerization stuff, right? Like, as best I can tell, this is pretty much only documented in this module. That being said, the documentation is quite good. I mean, like, this is a lot to be written about, but I think that, yeah, it's a lot of pulling threads. It's a lot of, I saw this term somewhere and I was curious where it came from, so I did a bunch of Googling. Could stand to be a little bit better, but
I'm sorry, I'm sorry, Joe. I was distracted for a second. When are you going to publish your book about low-level Haskell?
When I understand enough about low-level Haskell to actually write a book about it.
I guess you have a goal now.
I would say, by the way, actually, so this isn't so much a place you can go to get a good idea in one spot, but Andrew Martin and Daniel Cartwright are two people who are extremely knowledgeable about low-level Haskell programming. Well, I wouldn't recommend that you bother them directly as people because they have lives. I would recommend that you definitely check out some of their GitHub repositories because they are just a wealth of knowledge in this area.
Cool. Well, if there are no other questions, and I don't see any at the moment, I think we will formally close the official recorded meetup part of the evening. And if you want to stick around for a few minutes, we can have general chat if anyone wants to chat.
Before you do that, I did want to like close out with a couple of things, which is, first of all, Steve, like you said earlier, you know, I want to thank you specifically very much. When I moved to New York, I was just getting started in software engineering as a full-time profession, and I was mostly interested in Haskell, but I was reading through the Haskell Programming from First Principles book, and I hadn't really done much outside of the exercises. And so your group was a sort of really great way to keep me interested in the language, interested in sort of programming concepts that weren't just, you know, work related specifically. Encouraged a lot of us, I think, to go and try and do things like this, to speak at places. So I absolutely wouldn't be doing this type of thing without you. And so I just wanted to say thanks very much for the influence that you've had. It's been a very, very positive force. And yeah, I mean, I absolutely wouldn't be doing these types of things if not for that study group initially when I moved up here.
That's really nice. I mean, I can say the same for myself, even though I don't work, unfortunately, I don't work with Haskell. I transitioned into becoming a professional software developer, I think largely on the strength of having been exposed to so much programming and concepts about programming and just talented people, and just being around people who are doing it made me want to do it. I really think that this is something that can change lives. It's a bold statement, right? Haskell can change lives, but if you can find a supportive corner of the community, and I know that that can be difficult, it is the kind of language that rewards study and patience and practice, and all of the things that you say, they're very nice, and I'm virtually incapable of absorbing compliments. But I think we can both say that Haskell has changed our lives in some significant ways. You're writing it for a living, and I have become the lowliest creature of all, which is an engineering manager. But I don't think I'd be here if I wasn't somehow able to combine my my past as a teacher with my technical exposure. I don't know what else you could call it. So it's a privilege and a delight for me to still be able to maintain close relationships with all of the people I've met in the FP world, especially with you, Joe, and just to keep the learning alive.
Yeah, and then I think I also wanted to say thank you to you know, Richard Eisenberg for doing the initial work and for writing up these papers. The Levity Polymorphism paper is actually not, it's like, I think fairly decent to read, although I understand that that's kind of a weird, like, I feel like Haskell programmers basically all get to the point where we start reading papers and we're just like, hey, you should just read the paper. It's actually quite good. So I don't say that lightly. Yeah, the paper is quite good, but I feel weird about saying that. Like, it feels like I've hit a weird point where I can remember people who were writing Haskell before saying these things, and I was looking at them like they're crazy. And then
some of the papers are quite readable. I mean, I can't read all of them, but I've actually read quite a few, and I think it's a credit to the language that you can explain concepts in it so well.
and then I think also all the other kind of people that I drew code from, so like Daniel Cartwright and Andrew Martin have been two just extremely powerful forces in pushing through a lot of this stuff of make it possible to write Haskell that is extremely efficient, and you know, make it possible to take some of the abstractions we have in Haskell and express them without nearly as much runtime overhead. And to all the other people that have been working on GHC, I mean, you know, it's very easy to think about how GHC is a thing that exists and lets me write Haskell code and get things out of it. But it's crazy advanced. The compiler is just, it's like world class.
It's kind of amazing that it exists. I mean, really, who's making money supporting GHC?
Yeah.
Such a labor of love.
That's a whole other can of worms, but very much agreed there. I mean, I was even just thinking about things like, you know, the optimizations that GHC can do are quite impressive.
So Joe, now that you're famous, having appeared at the Berlin Functional Programming Group, what are you going to be doing next?
Next as in like
next project or next talk, or if you're writing anything, what are you doing? What are you up to? What's next?
And it's a really good question. I don't have a ton that I'm working on actively right now. Like, this was kind of nice because it was a good forcing function to get a bunch of my thoughts for the past 8 months together down somewhere. Mm-hmm. This is kind of weird, but like I'm starting to use Emacs to do more personal organizational stuff because I've had problems with to-do lists and like personal organization in general.
That does sound weird.
Yeah, I mean, I would also love tips of how other people manage this, but mundane life stuff, like how do I keep track of all of the papers or like bits of code that I've been reading so that when I'm doing something like this talk, I'm not stuck digging through, you know, months and months of bookmarks. So basically like personal life organization stuff, surviving New York City in the middle of a plague, also that.
Okay, I mean, these sound like good topics for our general chat. So why don't we say goodbye to the internet, and let me thank you one more time, Joe, for sharing your thoughts with us this evening, and we hope to see you again. And I hope to see you soon in person.
Thanks very much, Steve. Hope to see you soon as well.